we were going to talk about beyond tree decomposable graphs to decomposition recombination plans. So just to recall where we were, we had talked about how tree decomposable graphs have the nice property that, just to give you, remind you what a tree decomposable graph is. It's a graph that can be decomposed into 3 parts, each pair sharing exactly one vertex. That's the definition. And the base case is that the graph is an edge, right? So it's a recursive definition with a base case. So it has many nice properties, and there are nice algorithmic properties, which I won't talk about right now. But the part that we talked about was, just to remind you, maybe I should decrease the size a little bit.
Maybe if you click
so
Google Chrome.
The part that we talked about is that we can find a solution or realization of distances specified on the edges of the graph. By realization, it's point coordinates such that those distances are realized. Another alternative way of thinking about it is that you're completing the distance matrix, a partially specified distance matrix. Some distances are given, and you're trying to figure out what the remaining distances are, and the standard, it's equivalent to the problem of finding a realization, so that the remaining distances that are not specified are obtained by measuring the distances of the realization, the non-edges of the realization, and they're put there. So basically, realization and partial matrix completion are essentially the same problem. So now, of course, if they say find all realizations, then it's the equivalent of finding all completions and so forth. So anyway, this is just to recall. So if your tree decomposable graphs have the property that when you can sort of realize or find the point coordinates of one point at a time, or in this kind of situation, it's a little bit different than what I drew there. You're sort of having the realizations of the 3 parts, having found solutions of the 3 parts, you can find the positioning, the relative positioning of them, so to speak. So in other words, the position of that point with respect to these 2 points very quickly, simply by solving another quadratic, because you've solved this. So you have a realization of this, which means you have this distance, you have this distance, and so you have this distance. And so you just, the question of finding coordinates of this just corresponds to intersecting 2 circles, which is 2 quadratics. By the way, everything that we're talking about right now is in 2 dimensions, but the same idea of 3-dimensional tree decomposable graphs is identical. There's no difference, except that instead of having 3 of these guys come together, you'll have 4, right? And so in general, for dimension D, it's D plus 1. I just can't draw like that. So all examples that we'll be looking at will be just for D. So by the way, one important thing that I forgot to mention, which we did before, but now in the recollection I forgot to mention, is that because of this property, just this recursive property that we talked about, automatically ensures that these graphs are minimally rigid. Okay, so since you have been in Tony's class, you understand what minimally rigid is. And this is not a hard thing to prove. It's quite easy to prove. You just do it by induction, starting from the base case. The base case is that each one of these is an edge, and then you proceed from there. So it'll just become something like, it's not quite a Henneberg construction, but it's practically a Henneberg construction, Henneberg 0. Okay. And so essentially, we can, when we do some of the proofs, eventually when we talk about flexible graphs and we have to talk about their configuration spaces, we will revisit tree decomposable graphs. And at that point, we're going to do a little more detailed proofs about these constructions. How the Henneberg 1 type construction, how it helps us later for describing the configuration space of these things. But for the moment, it's very simple. You understand what it is, and I don't want to belabor the point. So the key idea, as we talked about, was that, this, what we showed here of solving one quadratic at a time, is essentially a triangularization of the original distance constraint system, which was a quadratic system, into, by triangularization, it means that we produce something like a matrix with all zeros over here, but these are all polynomials. They're not linear polynomials. They're nonlinear polynomials. But the idea is that these are the variables in the columns, and at any stage, you add one variable at a time. Okay. So, or in other words, you're solving a single quadratic in one variable. And I gave it as a homework a long time ago that saw, intersecting two circles, or, that you would need to produce this point, or intersecting three spheres, and so on and so forth. You can write as in this way, as a triangularized system where at each stage you're solving one quadratic in one variable. And this is the case, as I said, in any dimension. It doesn't matter. We're still following that very original algorithm that we had with the sphere intersections. And so the idea is that this triangularization, which you can do, by the way, for polynomial systems using Grosvenor bases and Wu-Rit characteristic set, or whatever it is, there's a standard way to find a triangularization. The problem is those triangularizations all end up with very high degree. So these as you keep going down, this last polynomial, univariate polynomial, will have typically exponential degree in the size of the original system that you had. But these particular examples, these distance constraint systems, if you sort of input the original graph, the constraint system corresponding to the graph. So here, for example, is the actual graph with the edges and so forth. And you have distances there, and you wrote the polynomial system down. The triangularization actually ends up maintaining the degree, preserving the degree. It doesn't bump up the degree like the, Grosvenor basis or other methods would do. So that's the key idea here with these tree decomposable graphs, that you can obtain a triangular system that keeps the degree as quadratic. And that gives you this radical, this kind of solvability by quadratic roots, square roots, as a tower of field extensions. Okay, so the advantages of, going back, the advantages of decomposable graphs, the triangularization of a polynomial system without increasing the degree. And then this you can think of as a recursive decomposition of the graph. Now thinking about the graph, we always go back and forth between the polynomial system and the graph, right? Generically, the properties of the graph will be used to talk about how many solutions the polynomial system has. We want finitely many solutions. As I said, these are all rigid subgraphs, rigid graphs, and everything that's immediate to prove from the description, the definition of tree decomposable graphs. So we decompose into a constant number, in this particular case 3, rigid subgraphs. And each one of those has finitely many solutions because they're rigid by generically speaking. And then now the new graph that you're creating after putting the 3 of them together is also rigid, also has finitely many solutions. And then we also know that adding one additional edge at each stage, one additional constraint, or one additional, the equivalent of one distance at each stage, then gives a unique solution. You reduce that finitely many solutions to a unique solution, generically. So these are the, okay, William, you have a question?
Yeah, are you able to hear us?
You have to, I can't hear you. Wait a second, have I? Yes, sorry. Okay, somehow I had the volume down. Sorry. Yeah.
Yeah,
Ask the question.
I was just checking because Alex was trying to ask a question, so I didn't think you could hear us.
Oh, right. Okay. Well, Alex, what's the question?
Okay, thanks. It was a little bit a while ago when you mentioned that
This one
Grosvenor
here?
basis would produce a
Yeah.
polynomial of high degree.
Mhm.
I'm guessing this is well, anyway, so, but when you're saying that you keep the degree at 2,
Yeah.
you're not finding all solutions, but just one.
No, you find all solutions. You solve that system. It's a degree 2. It's got 2 solutions, right?
Mm-hmm.
And then if you plug in either one of those 2 solutions or both, each one of them will at the next stage potentially give another 2 solutions.
Okay, so you do have to solve many degree 2 polynomials. Yeah.
Yes, but degree is all I'm talking about.
Right, and each stage has potentially 2 solutions.
Yes, and the number of solutions, by the way, you don't gain anything from Grosvenor basis either. It's the same thing. They'll also have at the end lots of solutions, and if you're back substituting, you're going to have to try every single one of them.
Right.
Okay, so
Okay.
that in that sense of number of solutions, there's no real. In this case, we actually can count in a way because the potential number, there's an easy upper bound on the number of solutions, which is 2 to the n, which is the number of equations.
Yep.
Where n is the number of equations. But the point is here that the degree doesn't increase.
Okay. But yeah. Okay, so it's just the degree of each polynomial
Exactly.
that you're solving. Yeah.
Exactly. The degree of each polynomial that you're solving remains quadratic.
Okay, thank you.
Okay. There are other advantages. They are nice polynomials because you're solving them in a simple way, right? I mean, I am just intersecting. It's sort of a nice quadratic too. In addition, there are other things, but I don't want to go into details about those.
In other words, I was just kind of, because you could view this as an algebraic variety with finitely many points, and then the degree of that variety is the total number of solutions, which is definitely not 2.
Just 2 to the n potentially.
Exactly, or something lower.
Yeah, it's the degree of this triangularized system. I think they call it the triangularized degree or something like this. Okay.
Which should potentially be the degree of that polynomial coming out of Grosvenor basis.
The number of solutions won't be a single polynomial coming out of Grosvenor basis anyway, right? From Grosvenor basis, it'll be the Bézout number that comes out of your original system. I mean, just to get the degree, which is essentially the number of solutions, as you point out, you can simply look at which is, you can just get the Bézout number, which we had in the last lecture.
2 to the n. Okay.
In this case, it'll just be 2 to the n.
Okay, thanks. That was helpful.
Yeah. So anybody else had a question? Sorry, I didn't have my sound on.
I think it was just me.
Okay. Yeah, by the way, yeah, you have to ask a lot of questions because Will told me that he had to meet some kind of admiral or something. so you have to ask all the questions, Alex. It's on you. Okay, so everybody should ask questions. I am just pointing to these 2 people who asked the most questions in general. So here, adding so this part maybe explains a little more, Alex, is that there are 2 solutions in general at each stage, finite number of solutions, typically 2, could be 2 or 1. But if you add in this additional edge at each stage, which means one more constraint, so which we also did in our original Euclidean sphere intersection algorithm, it reduces to a unique solution. Remember in the original sphere intersection algorithm where we didn't have a fixed dimension, in order to decide whether to increase the dimension at a particular stage, we looked whether we had 2 solutions or 1, right? And if we only had one solution, then it sort of signaled that you had to, if you had two solutions, it signaled that you have to increase your dimension at that stage. I'm talking about the original algorithm that we had to even prove the Cayley-Menger theorem, the similar algorithm that we're using here. So, but with that one extra edge, we actually get a unique solution. Here, the dimension is fixed, right? And this one extra edge business is the same for any dimension. You know, we fix the dimension at that dimension. You have a triangular 3D composable will involve typically d+1 distances. In this case, 3 distances, and the unique solution would then involve one more distance, so d+2 distances. So the disadvantages of this, of course, is that it's a small class of graphs. You know, it's not this particular, the graphs of these polynomial systems are very special. They are so simple graphs that don't have these properties. So basically, hang on, I think I should open a new slide. Actually, I'll open a, I want a new share. And I just want to show you some examples, very simple examples of graphs that are not 3D composable. So for example, you could have just the simple graph, you know, with two, this is called the C2 cross C3 graph, right? So this guy, or you could draw it this way if you want. This graph is a cycle of 3 crossed with a cycle of 2, and that thing is not 3D composable. So this is the classic. The reason I'm not mentioning another thing that you're all very used to, which is the K33. This is called C3 plus C2. The reason I'm not mentioning this, any idea why I'm not mentioning this one?
Maybe it's not planar? No,
it's not decomposable at all. Okay, so in other words, the only decomposition of this is by decomposable. It's not, you know, it's only a trivial decomposition where the graph, if you think of the graph here, you know, the only sort of rigid subgraphs inside it are the edges. So you've got the 6 edges. You know, you'll get all the 6 edges here. So you just got a trivial decomposition. Right, so which would be the case for, say, let's say a triangle or something. It's just got a trivial decomposition. But this has a non-trivial decomposition, which is the 2 triangles are both rigid. And there, you know, there are 2 rigid subgraphs, very clearly 2 rigid subgraphs here. And those are non-trivial. I mean, trivial is edges. So, so this actually has a non-trivial decomposition, but it doesn't have that form that we had for 3D composable graphs, which is this kind of thing. Okay, so there are many graphs in the slide. I had an example of, you know, you could have something like this, for example. That's 3D composable. Right, because you can recursively now you've got the three parts, and each of the 3 parts looks like this, and then there you can split them up into these 3 parts, that part, and that part, and then again, now these 2 parts are already at the base case, which are edges. Now you've got that one, so you've just got the triangle, and then the triangle is clearly 3 parts. Okay, so there are all kinds of graphs that are 3D composable. You know, they are pretty, you know, if you just barely look at the graph, basically they're non-3 connected. They could be 2 connected, but they're not 3 connected. 3 connected means that in order to separate, I mean, I should say maximally non-3 connected, which means it is 3 connected means there exists no way to separate the graph into 2 parts by removing only 2 vertices, right? But what we are now saying is that, in fact, any pair of vertices, in order to separate them, you can separate them with just removing two vertices, basically. So it's a little more, it's stronger than simply saying not three connected. Okay, so that's the class of graphs. And then this one has two non-trivial components here. And you see, we are starting to draw these kinds of pictures. And so for this, for example, I would draw such a decomposition picture that looks like this for this guy. So let's see, let me move this so I don't have the chat sitting there. So for this, I would have the graph at the root. And then I would say, okay, these three guys, go to blue. So the three guys are sort of the next level rigid subgraphs inside it. So there are three rigid subgraphs. And each of those rigid subgraphs is going to decompose in this manner. So again, they divide into three. And one of them is a triangle. It divides into three. Edge, 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 edge. And each of these looks exactly like this. So this part is duplicated in all of these places. Okay, so you can see that we are starting to draw the decomposition as a type of tree, right? It's not necessarily a tree in a way, because these, not strictly speaking a tree in the sense that the leaves don't share anything. I mean, there are leaves from here, leaves are edges, and the edges may share vertices, that can happen. And in fact, this subgraph and this subgraph shares a vertex, and this subgraph and this subgraph shares a vertex. So it's not a tree in the strict sense of, somehow the object here and the object here don't create any cycles. That's not what we're talking about in that tree. This tree is just a way to schematically representing the decomposition. Into rigid subgraphs. So this decomposition here is going to look like three, sort of, in the beginning, you've got two of these triangles. So each of these is a triangle. And then you've got a bunch of edges, three edges, 1, 2, 3. So the edge, edge, edge. And each of these is a triangle. So it's got edge, 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 three edges, and this one's three edges. Okay. So that's so we are starting to think about, a graph in terms of a type of a recursive decomposition of the graph into rigid pieces. Notice that we are also not talking about very trivial decompositions, because if you simply say decomposition of the graph into rigid pieces, you could have given a sort of a trivial decomposition of this graph by simply right in the beginning, just putting the graph and then putting all its edges. So how many? It's got 5 edges, 15 edges down here. I could have put 15 edges down here. If all I said was I want to decompose the graph into rigid pieces, then I put all the 15 edges. That's not what we're doing. We are decomposing in the graph so that at the children, so to speak, of the full graph in the tree, these children are themselves sort of rigid subgraphs that are maximal proper subgraphs of G. So this is a maximal rigid subgraph, proper subgraph inside G. And so is this, and so is this, right? So that the decomposition is somewhat, for the tree decomposable case, this follows the definition. It follows the definition. It says the graph divides into 3 parts, each one of them, which is rigid. And we know that those 3 parts are themselves maximal proper subgraphs inside G. Here we've done the same thing. These are these are the 2 triangles. They are the maximal proper subgraphs inside, and so forth. So for K33, what we have here is the maximal proper subgraphs that are rigid inside it are in fact just the edges. Okay, so this we could say it's not tree decomposable, but it's kind of pointless because it's only decomposition in any way, shape, or form is just the trivial decomposition. While this one has a non-trivial decomposition, but it's not tree decomposable. Okay, so this thing has a non-trivial decomposition, C2 cross C3. That's not tree decomposable. Not tree decomp. Okay, so for the longest time, people in the CAD community, computer-aided mechanical design, computer-aided design community. So let's see, how do I new share? This community, new share. This is the one I want. Why is it giving me this weird thing? I have no idea. What are you seeing, guys?
We still see the diagrams you've been drawing for a while.
Okay.
You want a new screen?
For some reason, when I say new share, and I see the screen that I'm trying to share is not showing me on the screen. I mean, it's not showing it to me on the screen. Weird. Okay. So now, so you're seeing the slide that says triangularization with quadratics and radical solvability?
Yep.
Yeah, you're seeing that screen. Okay. You're not seeing the screen that I just drew on a moment ago.
No, we don't see that anymore.
Okay, good. Okay, so the disadvantages is that this is a very small class of graphs. There is a theorem, famous theorem by Owen and Power from, I don't know, 2006 or something, that says that such graphs are exactly triangle decomposable graphs, in other words, are exactly those for which you have this type of a triangularization by quadratics. So it's called quadratically radically solvable. But the theorem doesn't go all the way. It only proves this for topologically planar graphs. So in other words, the K33, which we know is not topologically planar, well, that in that particular case, there's no interesting theorem to prove, but it, you can think of other three connected graphs, which are minimally rigid, decompose nicely and so on and so forth, but they're not included in this theorem. The conjecture is that you can remove that condition of topological planarity and still prove the theorem, but nobody has done it so far. So in any case, I just wanted to say that it's a very small class of graphs because there are tons of polynomial distance systems which are not of the form that you can express the solutions in this extension field where you add one square root at a time. This is a very small class, Galois theoretically. Okay, so this is, for example, another graph which is not tree decomposable. As you can see, we have, essentially you've got the C2 cross C3 sitting here. You see, there's a triangle connected by three edges. It's not quite the same C2 cross C3 that we saw, but it's more or less the C2 cross C3 that we saw. And then it's connected. But this part alone, by the way, is in fact triangle decomposable because you could decompose it in a different way that would cause. So for example, you could have taken the central part, just this triangle here and this edge and this triangle here. This entire rigid subgraph here, which is this quadrilateral with a diagonal. You could have taken that one and this edge and that's a triangle decomposition, tree decomposition, and then proceeded in that fashion. But so this one is not, and the putting them together by adding these two edges would also, these three edges also prevents that from happening. So this is a non-tree decomposable graph, and the important thing in this slide is it's showing that this decomposition that I talked about is not necessarily unique. Okay, it doesn't appear, it doesn't clearly look unique, because here's two such decompositions that I have drawn here that are both possible. Okay, so now I want to take a step back and remember this quadratic system that we're trying to come up with, right?
Hey, Meera,
Yeah,
on the previous slide,
yeah.
Is there anything that that we can say, for example, like the on the left and the right, they seem to have different length paths from the top node to the leaf?
Yeah, there are other things. So if you introduce this maximality condition that I talked about, right, a moment ago, you want the maximal subgraph, maximal proper subgraph. If you put that condition, then this won't be a possibility, because now you don't have maximal proper. This is a maximal rigid subgraph. You see, but
So
without that, yeah.
Will the length of the longest path be invariant?
No,
Under different
none of these things is
decompositions?
invariant. I mean, in general, non-trivial decomposition, by which I mean anything that's sort of doesn't just decompose into edges. They can be widely different. In fact, we will talk about that. There's a problem of optimizing or finding a decomposition that minimizes not the measure that you're talking about, which is the length from the root to the tree, root to the leaf, but minimizes the maximum number of children of any given node, because that sort of it dominates the algebraic complexity of solving the system eventually, right? We want this. If you think of a triangularization, we would like it to be as close to being just a triangular system. We're allowing a block triangular system maybe, but then we want the number of polynomials that you're simultaneously solving at any given time to be as small as possible, because that's where the complexity blows up.
So if we have 3 children,
yeah,
then in the plane, that'll be good?
3 is good in general.
What are the other numbers, and which ones are good and bad?
Anything bigger than 3 just starts becoming problematic, but may be unavoidable depending on the graph. Okay.
Is there some connection between these two pictures? Like
they're both decompositions into rigid subgraphs.
No, I'm talking about the upper level, the origins.
Here?
Is there some function that can take me from the left one to the right one?
They're
so
the same
similar.
graph. They are the
so
same
similar.
graph.
Pardon?
They are the same graph.
The same graph?
Yes.
How can they be the same graph? There is a circle here.
No, the circles are not the graph.
Circle.
The circles are showing the rigid pieces, rigid subgraphs of the graph.
Okay, the left inner circle, if I stretch it, I get another extra circle here on the right side.
First of all, I would like you to understand what the graph is. The graph is these little these little vertices. These are the vertices of the graph, and the edges are here. So the graph on the left and the graph on the right are identical. They are the same graph.
Okay, the same graphs, but the circles.
There's an
extra circle here.
The circles
on the right side.
The circles represent rigid subgraphs of the original graph.
Okay, I'll think about it. Thanks.
Okay, so this is a rigid subgraph, but this is also a rigid subgraph.
Right.
Okay. So I'm not, at the moment, I have not put that additional condition that I mentioned to you a moment ago, saying that I want the children of a given, or the subgraphs chosen of a given subgraph, of a given graph, to be maximal proper subgraphs that are rigid. I have not put that condition. So for example, this is not a maximal proper subgraph of the original graph that's rigid. This could be a maximal proper subgraph that's rigid. Yes, in fact it is. So this thing here is in fact a maximal proper subgraph that's rigid.
So it's
But
maximum.
even if
Hi, Meera.
yeah.
So it's maximum rigid in dimension like the v minus 1. So the number of vertices is -1.
It's in this case it's just 2 dimensions. It's at the moment we're talking about the whole thing has moved to fixed dimensions. We're talking about a fixed dimension, and this particular example that I have drawn here, and most of the examples that I'm drawing, because I'm unable to draw graphs that are triangle decomposable or whatever in more than 2 dimensions, I'm only drawing 2-dimensional graphs, 2-dimensional constraint systems.
Okay.
So I'm only talking about rigid in 2 dimensions.
But then if you have a for your S7, then you add one node. This is like
yeah, you're probably right. Yeah, you're right.
Right?
Yeah, you're right. I'm not seeing the picture correctly. You're right. That's in fact, since this is connected by 1 node, so all of these are also a maximal. So in fact, neither one of these decompositions is maximal. I mean, ensures that the children are maximal. So you're right. In this case, I don't know what this vertex is, but you could have taken, for example, this entire thing, excluding only this vertex, and that would be the maximal maximal proper subgraph that's rigid.
Yeah.
Okay. You're right. Yeah. So in this case, both of these decompositions do not have that extra condition that I mentioned.
Okay. Yeah.
But they do decompose into rigid subgraphs. That's true in both cases.
Okay.
Okay.
Yeah.
So in both cases, all these nodes here, the children of this represent these 2 big circles, which are both rigid. And here they represent that one and that one, which are both rigid, and so forth. So they're both decompositions into rigid subgraphs, but they're not decompositions into proper vertex maximal subgraphs. Yeah. Okay. Right. So anyway, stepping back a second to what we want sort of algebraically. We want to ensure that every time we're picking a small, and when I say solvable subsystem, I mean it's got finitely many solutions, which is, we understand that as rigid, generically rigid. So rigid graph for that dimension. Okay, so we want to pick something that has finitely many solutions, which means rigid, and then in a way solve it or do somehow replace it by a smaller subsystem, so which I call a simplification of Ti of Si, and replace it into the original system EI. So currently you have a system, overall polynomial system EI, and you're taking a small piece of it, and which you're guaranteed has finitely many solutions, a subsystem, a direct subsystem of it, which means a subset of equations with those variables. Yeah, that's what I mean, a direct subsystem of it. And then you do something to solve it. I mean, you want it to have finitely many solutions. You can replace it by something else which is simpler in the simplification to get the next big polynomial system. And what the key thing you want is, you want somehow the set of real solutions of the new system to be preserved. Okay, so so if you go here, this is just a simple picture saying I find a subsystem which has finitely many solutions. You simplify it somehow and put it back in there such that you're not changing the set of real solutions of this one. And then you find another subsystem here, simplify it, and then you get a new system and you find a new one, and so on and so forth, right? So the second transformation that simplifies this system might also end up simplifying the previous one. That's fine. Okay, but the key thing is you're preserving real solutions as you proceed. So this is essentially a schematic of how you do this. We have linearly ordered this, but it doesn't have to be a linear order. I mean, you could pick S1 and S2 at the same time, for example, if they don't, if you can keep the other conditions of simplification and so forth, preserve those. Okay, so these are some kind of subsystem simplifiers. So if you look at the desirable properties of the decomposition, essentially we want to make sure that these transformations or simplifications that you do, preserve subsystems. And if you apply this transformation to two different subsystems, it's the same as applying the transformation to the union of those subsystems. If you apply the transformation to the intersection of these subsystems, then by intersection, I mean induced. So if you have a subsystem and another subsystem, the intersection would be, a subsystem of a subset of equations, that belongs to both of the original subsystems, and a subset of which is supported on a set of variables which also belong to the original subsystems. That's what I mean by union and intersections of subsystems. And sorry, I apologize for that. Okay, so and the other thing I want is that the overall system at any given stage, EI, which is the overall system, you can sort of split it up into three parts, which is the subsystem that I picked up, the solvable subsystem or has finitely many solutions, union, some kind of a part that is shares some shares some variables with it, and another part that doesn't share any variables with it. Okay, and so this is solvable. Ri is a maximal subsystem such that Si and Ri don't share variables. Ui shares some variables, and all three of them do not share any equation. So in other words, the set of equations has been split into three parts. These two don't share any variables. These two Ui may share some variables with Si and Ui. And for any A subset of Ri, you also have that the transformation or the simplification applied to A gives A itself. Okay. So in other words, the simplification at any given stage only simplifies Si. And it may simplify Ui somewhat, but it does not simplify Ri, which does not share any variables with Si. And then we also have the pre-images of these. If you just keep taking the pre-images of Si, you can get essentially you can get all in. All it's saying is that you keep, essentially you preserve the set of solutions. Okay. So what we would like to do is these properties, we would like to sort of write them down generically so that, and express them graph theoretically. Okay, so that's the idea of how this whole DR, decomposition recombination plans came about, which is that here's what we would like to algebraically decompose. This is how we would like to algebraically decompose. And we want to sort of do this generically beforehand by just looking at the graph. We get a decomposition just based on the graph. And then after we have decomposed, now we have a polynomial system, which we have decomposed based on some properties of the underlying graph. And then now we solve the polynomial system. Hopefully it gives us some kind of block diagonalization where the blocks are not too big. Sorry, block triangularization of the system so that the blocks are not so big, and then we solve it. So that's the overall strategy, right? So again, to repeat, we want to recurse. Whoops! Somehow it's very sensitive to my fingers moving on the pad here today. Okay, so we want to recursively decompose the system into separately, independently solvable subsystems. To do this, we know, so in this picture, we could do S1 and S2 together, but as we want them to be somehow solving S1 or simplifying S1, we don't want it to interfere much with S2. So to do this, we no longer care about the system, but only the underlying combinatorics or the graphs. So here I say hypergraph because this particular talk was prepared in a slightly more general setting than just distances. Right now, we're only caring about distances. So just think of it as a graph. And so we can use combinatorial rigidity to translate this, having finitely many solutions, generally having a solution, or generically having no solutions or just one solution, into properties of, so overconstrained doesn't necessarily mean just one solution, but generically, if you think of having more equations than unknowns, unless those extra equations are somehow consistent with the others, the ones that they depend on, you will have zero solutions. So, okay, so other uses of this DR planning, by the way, is decomposition, recombination planning. All this means is that you have a polynomial system to solve, but you're going to look at the graph underlying it and beforehand come up with some kind of a decomposition that has the properties that we talked about 2 slides ago. Okay, so so the uses are, you can sort of, by looking at the DR plan, get a sense of how difficult it's going to be to algebraically eventually solve the system. If the graph is under constraint, which means flexible, and this is where we're going to spend a little more time later, more deeply on the properties of tree decomposable graphs and others for which these completions, by which I mean it's not like the partial matrix completion. This is slightly different. What this is saying is the graph is not rigid. I want to add enough edges so that it becomes rigid, right? So and I want to add them in a nice way, and we can define nice later. And so and these new edges that you're adding can be used as a kind of parameters to understand the infinite or more than 0-dimensional configuration space of this under constrained graph. Under constrained just means not rigid, right? So independent and not rigid. So the other thing is, you have dependent edges or dependent constraints, and we want to have some way of removing these dependent constraints or recognizing them and removing them if needed. And this DR plan helps you do that as well. And finally, you want to allow, sort of a decomposition. The decomposition into subgraphs of this type allows you some kind of underlying decomposition of the rigidity matrix, the stress matrices, and the flex matrix. You've seen all of these in Tony's class. Okay, so your recursive decomposition of the graph into rigid pieces allows you to sort of recursively decompose the rigidity matrix, the stress matrices, and the flex matrices. So it has many uses, and it's a heavily used concept now in computer-aided design and other fields that do this on a regular basis.
Meera?
Yeah?
What's a flex matrix?
The right null space of a rigidity matrix.
So just the kernel of the rigidity matrix is a subspace.
The kernel of the rigidity matrix is another matrix. Yeah.
Well, so you choose the basis and write it as a matrix. Okay, I see.
Yeah. All right. Yeah. So they just like they call well, stress matrices are slightly different. They're not just putting together the stress vectors into a matrix. You write the stress vectors in matrix form. You could do a similar thing for flexes, but in either one of those cases, it doesn't matter. Or whichever way you want to think about it, whether you want to think about it as just putting the stress vectors down as rows of a matrix, or putting the flex vectors down as columns of a matrix, or you want to think about writing the stress vectors as a stress matrix, or flex vectors as flex matrices, whichever way you think about it, you get decompositions from the DR plan. Okay, so now I can sort of define, you will see in different papers, the DR plan is defined slightly differently because which of these conditions have been imposed is not clear. Okay, so the original DR is not always uniform, is what I'm trying to say. So you have to sort of pay attention to this. So here, just a DR plan just says that each node is a rigid subgraph of G. So in fact, it's not saying that it should be rigid maximal proper subgraph. It says no, that it doesn't say that. So you could in fact have that trivial decomposition that I had where the K33, I divided it up into all the children. Well, in that case, that's the best you could do, but I could have taken even C2 cross C3 and divided up into all the leaves, which is the edges, and that would perfectly satisfy this definition. Root node is a maximal rigid subgraph, an internal node is the union of its children, and a leaf node is a single constraint, and in this case, it's a single edge, which is a single distance. So that's the definition of a DR plan of in our case, just a distance constraint graph. And it could be a forest because, in this description, we're not starting out with any assumption that G be rigid. So if G is not rigid, it's going to end up with multiple roots, so to speak, each one of those being the maximal rigid subgraphs. A root node is a maximal rigid subgraph of the graph. But if you started out with G itself being rigid, you'll have a tree kind of thing with a single root node. Okay. Here's an example DR plan. The simple tree decomposable case that we looked at. This is a perfectly valid DR plan according to this definition. You could just split it up into your 9 edges, or you could have a slightly nicer DR plan here in a way that splits it up into the 2 maximal rigid proper subgraphs, which are the 2 triangles, and then 3 edges and so forth. So both of those satisfy the properties of in the definition, the conditions in the definition of the DR plan. Okay. So now an optimal DR plan is one that actually minimizes the maximum fan in. By fan in, I mean, here's a tree. So we have a tree here. And a fan in is the number of children that the fan in for a given node is the number of children it has. And minimizes the maximum fan in means it minimizes the maximum fan in over all the nodes in the DR plan. I want to use the word nodes for the DR plan rather than vertices, because the vertices are the vertices of the graph. And the nodes are the vertices of the DR plan. So I just want to keep that separate so that we don't get confused.
Hey, Meera.
So, yeah.
If there's a fan in of 2 at a node of a DR plan, does that mean that we have a flexible graph?
No. It just means that they could, so look at this. So if you go back to this, it says nothing about how much the children overlap. So it simply says each node is a rigid subgraph of G. So you could have 2 nodes which have a lot of intersection. Okay, so just having 2 doesn't mean that it's flexible. So for example, you could have 2 rigid subgraphs that intersect on in the case of D equals 2 on a triangle, then, or 3 vertices, then the result is rigid.
Okay, so tree decomposable had like 3 subgraphs that intersected each pairwise at one
vertex. Exactly.
This is not. This hasn't none of those requirements are here.
None of those. We are generalizing well beyond that because the 3 decomposable class is a very small class. Okay.
Okay.
So so an optimal DR plan is something that minimizes the max. One thing that what we know is that even if you have completely solved the 2 subsystems of a given system, or so found all the solutions, finitely many solutions, we do want them to be rigid. So there's generically finitely many solutions for each of the subsystems. And if you have solved them, getting the solutions for the parent is directly, the size of the system for the parent is directly proportional to the number of children, which is why you want to minimize so in other words, in the block diagonal, if you do a block triangularization, the blocks, the sizes of the blocks are directly proportional to the number of children, So what we want to make sure is that those sizes of those blocks are small. So which is why you want to, an optimal DR plan minimizes, for some reason, this is jumping around, minimizes the number of children across all the nodes.
And Meera, can I ask another thing?
Yeah.
So maybe you can go back to slide 107.
Slide 107. Okay. Why is it jumping around like this? I have no idea. Okay, this one? Yeah.
Yeah.
Hopefully
is there any requirement? I don't see a
requirement,
requirement
right?
that the parent can be produced from its children. So if you know realizations of the children, do we require that the realizations of the parent can be found from its children?
Yes, that's what we're trying to get at. So remember that original algebraic conditions that we had. I don't know why this. Anybody have an idea why this is jumping around so much?
No. You could go to Google Chrome and try to make it full screen.
I did. I had full screen a moment ago. So, but now maybe it's better behaved. I don't know.
No, I mean, if you're literally in the Chrome menu, if you click View.
Oh, you mean just go to Present or something?
Well, no, actually. If I just click View and then I click Enter Full Screen, sometimes that's okay.
Oh, okay. Hopefully this has stopped now. I'm hoping. Okay.
But either way, I don't see that requirement in this list. Is it?
This list is it's trying to write the original algebraic conditions purely in terms of graphs. So the internal node is the union of its children is probably what you're trying to get at. By union means an internal node is a graph. The children are all subgraphs. You take the union of the subgraphs of the children, you have to get the original graph.
Okay.
Take the union of vertices, take the union of edges, then. Yeah.
So is this the definition of DR plan, this slide, or was it somewhere else?
This slide is the definition of DR plan. We will come to this, adding this extra condition about maximal subgraphs in a minute. This is the most commonly used definition. Sometimes they automatically add this maximality condition to DR plan, but it's not usually necessary.
So a leaf node is a single constraint. That means one edge, because we have a DR plan of a graph.
This is.
And the nodes are sub.
Yeah, I'm using some old slides, which is doing something more general than just our graphs. So think of our usual graphs, where every edge represents a distance. Yeah.
Yeah.
Yeah. And so these are single edges that represent one distance. Yeah.
And the involved primitives?
Where is the involved primitives? Oh, involved primitives are the vertices.
Like the coordinates of the vertices in the plane.
No, sorry. Yeah, I should have changed the slide. I'm sorry. So this is just because we're talking in general about hypergraphs, this constraint could involve more than two vertices. That's why it says involved primitives, but they're just, in our case, it's an edge and the corresponding two vertices. That's it.
Okay.
So in all the pictures, that's what we've got. It's an edge with two vertices.
Okay.
So the leaves are all edges.
Okay, and there's no requirement right now that the parent can be produced from its children.
What do you mean by produced from its children? We
that
need
the realizations.
The parent is the graph, which is the union of the children graphs.
and its realizations do not need to be produced from its.
There is nothing about realizations at all in this. This is purely graph theoretic.
Okay, thanks.
Okay, so this is purely graph theoretic. It's a statement about graphs. And we're going to try to show you later on, we'll try to show that this is enough generically to give the properties, algebraic properties that we talked about earlier, which is that we preserve the set of solutions as we go.
Okay, thank you.
Okay. Any other questions? This is just, sorry about this terminology here with constraints and primitives. This is just a single edge. That's all. Leaf node is a single edge.
Hi, Meera, when you say a graph underlying a polynomial system, what is that?
The underlying polynomial system in our case would be a distance polynomial for this edge, which says because in 2 dimensions.
Yes, I heard you said a given polynomial, find the graph or something, a given polynomial system, find a graph.
Yes.
Underlying, like, so there's a graph for any polynomial system.
We are at the moment only talking about distance constraint systems.
So it's not arbitrary polynomial system.
There are, I mean, if it comes from a system of geometric constraints, then yes, we do have a decomposition of those systems using the same ideas. The ideas generalize. So if you have, I mean, later on, I will show you other examples of constraint systems, but we're not going to get to that till the very end of the class, I think. Let me see in my own thing here. So rigidity beyond distances, beyond distance constraints. So we won't get to that until we get here.
Okay.
Everything from now to then are going to be only distance constraint systems.
Okay.
Okay, so whenever I say polynomial system, you can assume it's a bunch of distance constraints. Distance polynomials representing distances between pairs of points. Of course, the dimension may change.
I see.
Okay.
Thank you.
Yeah. But you'll see that even tree decomposable graphs, there are many examples of general geometric constraint systems which involve other types of constraints, which can be written as tree decomposable graphs. We'll get to that eventually, right? But I don't want to clutter our thinking right now because we have been keeping this only distances so far, distance matrices, Euclidean distance matrices, Cayley-Menger and so forth. So let's just stick to distance constraints for the rest of the class until we get to the end, okay?
Okay.
Yeah. Okay. Okay, so here's where we were. So here's a graph, and we have divided. These are 2 DR plans satisfying the conditions of the definition of the DR plan. And optimal is it minimizes the maximum fan-in, and it turns out that finding an optimal DR plan is NP hard. And it's a very simple proof that takes a reduction from the clique problem. And it's in a paper that we wrote some time ago. So next talks about history. So in the 80s, this idea of triangle decomposable graphs came about simply because of its nice properties, the ability to solve the corresponding underlying distance polynomial system, distance constraint system, and that it had this quadratical radical solutions, at least in most planar graphs, and believed to be the case for other graphs too. And one direction is straightforward, by the way. If it's tree decomposable, all tree decomposable graphs, planar or not, are quadratically radically solvable. It's the other direction to show that in order to be quadratically radically solvable, you should be tree decomposable. That, sorry, this should have been tree decomposable. 3 decomposable systems can be triangularized. Yeah. So to go in the converse direction is where you need the planarity so far. I mean, but it's believed that the converse also holds without planarity. And we used to, so they struggled after 3 decomposable trying to generalize, was kind of using various combinations of things, and the different things were confused in a way. The ability to find rigid subgraphs was confused with finding the DR plan. And then we sort of came, and this is my grad student, by the way, and this is a collaborator. We collaborator from computer aided design community. So we formalized this idea of decomposition recombination plan, which has since been very widely adopted at least in the computer aided design community. And so we separated the algorithms that find the rigid subgraphs from getting the decomposition, right? So assuming there's an oracle, so to speak, if you've been in an algorithms class or theory of computation class, you've used the word oracle. So assuming that there is some magical thing, which if you give it a graph will tell you whether it's rigid or not for the correct dimension, you can then ask, okay, how do I do the decomposition? Assuming the existence of this oracle. So we sort of separated the parts, and we said, okay, here's what we gave 2 papers. One talks about sort of what is it that we want algebraically, and then how do you capture it graph theoretically, and then give some algorithms for coming up with these decompositions. So they're a 2-part paper. And this slides are from another paper, which was a later paper with my grad students, which essentially cleans up gives an alternative way of thinking about these DR plans in the algorithms, the original algorithms from Hoffman-Lomonosov Sitharam did a bottom-up kind of building up of the DR plan. And this one does a top-down building up of the DR plan, which means it starts the graph, splits it up into parts, and then splits it up in parts and so forth. And these were sort of building it up bottom up. But both use this idea that there is a rigidity detection oracle. Okay. So for this paper, I preferred to talk about the later algorithm, this top-down algorithm first before we talk about the bottom-up algorithm, simply because it's a lot easier to understand. Okay. So the top-down algorithm works if there is an underlying abstract rigidity matroid. These are the conditions under which it works. So what does work mean? Depends on having an algorithm versus having a certain complexity. So the top-down algorithm, which is what we're talking about now, it's a later paper. I'll give you the references in the Piazza or add them to the slides later. It requires an abstract rigidity matroid to actually prove the things we're proving, sort of the structural theorems we're proving about the system, about the decomposition, to show that it is if the original graph is independent in the d-dimensional rigidity matroid, we achieve this algorithm will achieve optimality. And if we have an underlying sparsity matroid, which we have in 2 dimensions, but we don't have, we have no idea what it is in higher dimensions, then we get actually a polynomial time algorithm. So what I mean is we can give a definition of a DR plan with some extra conditions, which has certain properties, and the properties all go through if the first 2 are true, if it has an underlying abstract rigidity matroid and is independent, but doesn't, if it has a sparsity matroid, we get actually get a polynomial time algorithm. Okay. Let's go to the next one. Okay, so this structure that we're going to talk about now adds this extra condition that the children of any given node are in fact vertex maximal proper subgraphs that are rigid. And we call them rumps because they're so long. Okay, rigid vertex maximal proper subgraphs, RVMPS, we call them rumps. Okay, so we have two additional properties. First of all, the children of any given node are rigid vertex maximal proper subgraphs. And then the second thing is basically comes from the abstract rigidity matroid condition, is that if talks about the intersections between pairwise intersections between these rumps. So if all pairs of them intersect trivially means the size of their intersection is D, whatever D is, D minus 1 or fewer, right? So that's trivial intersection. So in case of D equals 2, the intersection would be 1 vertex, and D equals 3, the intersection would be 2 vertices, and so forth. Otherwise, exactly 2 that intersect non-trivially, all of them are children, otherwise exactly 2 that intersect non-trivially are children. Okay, so in other words, what this is saying is that there is either 2 children which may or may not intersect non-trivially, but if they do intersect non-trivially, there are only exactly 2, and otherwise every pairwise they intersect trivially. And trivial intersection, as I said, was the size or the number of vertices in the intersection is 1 less, at most 1 less than the dimension. Okay, so in the case of tree decomposable graphs, for example, the intersection between any pair is 1 vertex, and that's a trivial intersection. Okay, and in 2 dimensions, in order to be a non-trivial intersection, the intersection should contain at least 2 vertices. And you know this condition from the abstract rigidity matroid, that in general, if you have 2 rigid graphs and their intersection is greater than or equal to D, if they intersect on more than D vertices, D or more vertices, then the result is also rigid.
Hey, Meera.
Yeah.
So this condition 2 is what I was thinking about before. Mm-hmm. This guarantees that knowing the realizations of the children will give you realizations for the parent.
I don't think so. I don't think you need this. I think just the DR plan guarantees that, because simply you're maintaining all the union of all the children are part of the parent. Give the parent. The parent includes all the constraints in the subgraphs of the children. I don't think you need this. This is just, these are additional ones that help prove optimality and other things like that.
Okay.
So notice that at this point we're not we've sort of moved into a purely graph world. We're going to have to tie it later to the algebraic world so when we say decomposition and recombination, the recombination part is, okay, now we have we've found a DR plan, and now we have to take the corresponding distance polynomial systems and put them together and get the solutions, right? So that's the recombination part. We'll come to that later. So at the moment, we're living in a graph world, and we are defining certain graph decompositions. And we want to see, and we have defined the optimal DR plan purely using a graph theoretic way. And now we're going to try to ask, can we get this optimal DR plan fast? For that purpose, we're defining an extra condition on the DR plan, which we call canonical DR plan, which these are the 2 extra conditions. So this nice theorem is what we showed. which works whenever the graph has an underlying abstract rigidity matroid. That's what this intersection thing is based on. So what we say is that a canonical DR plan exists for a graph, and any canonical DR plan is optimal if the original graph that you started out with is independent in that d-dimensional rigidity matroid. Okay, so we are, today what I want to do is give a quick overview of the algorithm itself and the idea of a canonical DR plan, how that helps with the algorithm. But in terms of actually proving it, we're going to do that later, probably in the next class. Okay. So I might also spend a little bit of time today in talking about the bottom-up algorithm instead of the top-down algorithm. We'll come to that later. I mean, later in today's lecture. So when we, the importance of the canonical DR plan, we restrict the space of DR plans to this special class of, instead of thinking about all DR plans, we're only looking at the special class. So in this example, as you can see, it's basically 3 C3 cross C2s, the familiar C3 cross C2s, all of which intersect on a triangle here. And if you ask yourself, what are the maximal proper, rigid subgraphs here, you cannot, these are maximal proper rigid subgraphs, because if you take this one, then the only thing you've got is these 3 guys attaching to a triangle. So these are the maximal proper rigid subgraphs, one of them. And then the other one is this one. There's a third one, which is this one and this one. But the canonical DR plan says, in that case, if the intersection is non-trivial, you just take 2, any 2, doesn't matter. So we have taken this one and that one, 2 of those. And they intersect, as you can see, on the entire middle part. This entire middle part is common between the 2 of them. Then you split those, each of those, into their maximal, 2 of their maximal, which also have non-trivial intersections. And this one again, 2. And we, they happen to share this is their intersection. And the intersection happens to be one of the subgraphs in this case. It's drawn like this, but we could have just drawn it like a tree with this intersection sort of appearing twice here and there. And then after that, there's not much you can do. The maximal proper subgraphs are these triangles and the edges. And so that's what it looks like in all of those cases. So this is a DR plan that sort of satisfies this canonical property. And we want to, as you can see, there is in order to get the optimal DR plan. So the goal is to get this, where was the optimal DR plan? So the goal was to get the optimal DR plan that minimizes the maximum fan-in. So intuitively, it's kind of clear why you want to choose maximal proper subgraphs of a given graph, because you want the minimum number of children coming in. And you know that the children have to basically cover, because union of the children and the parent, the children have to cover the parent. So, so that's where the intuition of doing this canonical thing comes from. And what we can show, so we will eventually prove this theorem that a canonical DR plan exists for a graph, and any canonical DR plan is optimal if G is independent in the d-dimensional rigidity matroid. So just these 2 is sufficient. We'll prove that later. But as I said, today I would like to sort of motivate why we want to go through, it's a graph theoretic kind of proof, and why we want to go through that proof. Because the canonical DR plans give us an optimal DR plan in a fast algorithm for finding an optimal DR plan. Okay, so now the theorem says, if you have a good oracle, so that's what this underlying sparsity matroid is talking about. So you could say either that there is an underlying sparsity matroid, therefore you can get using Pebble Game or Network Flow or whatever, recognize rigidity quickly. Or you have an oracle. I mean, I could have changed the star to, provided there exists an underlying sparsity matroid, or there's an oracle for detecting rigidity, d-dimensional rigidity of a graph, either one of those two. Then we have computing an optimal DR plan for a D independent graph in whatever dimension has complexity order V cubed. Okay. So another, as a byproduct, we also get that this finds minimum and maximum non-trivial rigid subgraphs of the input graph, which are also shown to be NP hard in the same paper in general. Okay, by minimum means sort of finding a not just a minimal non-trivial rigid subgraph, but actually one that has the fewest number of vertices. Believe it or not, that's a hard problem. So I give you a graph and I want you to find sort of the minimum sized subgraph in it, which is non-trivial, which means it's more than an edge, let's say, and is rigid. That's a hard NP hard problem. Finding the maximum one, again, not maximal, but maximum, which means among the maximal ones, one that has the most number of vertices, is also NP hard. All of these problems are NP hard, or optimal DR planning is NP hard. All of them is generally NP hard, but we can show that using this notion of canonical DR plan, we can get it down to order V cubed for independent graphs, assuming the existence of a rigidity oracle, rigidity detection oracle. Okay, so there, for doing this algorithm relies on yet another twist of a canonical DR plan, which we call a pseudo-sequential DR plan. So it is a canonical DR plan, split up, I mean, with a twist. So here's a canonical DR plan. And what we're going to do is essentially think of the, we're going to create a DR plan which takes one of the two non-trivial rigid subgraphs, one of the two, rigid subgraphs with non-trivial intersection, and thinks of them as, splits them up completely into the next level, right? So this one at the next level is going to split into, it's going to split into all of these components. So in other words, here we've got the two rigid subgraphs with the non-trivial intersection. We keep the non-trivial intersection in one of them, and then in the other one, the intersection has now become part of the left subgraph. So this is the remaining part, and the remaining part is just, you think of it as just split into its next level. Okay, so again, here you've got two parts, and they intersect on the triangle. Sorry, you keep the one of them, and then the rest of it is just the triangle with the three edges here. So this is the sort, think of it as the remaining part. So whatever you keep, this is all the remaining stuff. Remaining stuff decomposes like this. So if you think here, you take this, what is remaining? What remains is these three edges plus this triangle. If you just take those three edges and this triangle and think of that as a graph, it's under constraint, of course, but it splits up. This is how it splits up. Similarly here, you take this, and then you take the remaining part, which is just, again, the three edges with a triangle. That's under constraint. It's a flexible, it's a non-rigid graph. And this is how it splits up. And so this is a regular DR plan for that. So if I just want to point out for you that the canonical DR plan also doesn't offhand, what is the definition of the canonical? You remember the DR plan itself doesn't require the original graph to be rigid, the starting graph. So it could have, the DR plan might end up with multiple roots. And this is the same thing. I mean, canonical DR plan doesn't require that the DR plan has a single root. It could have multiple roots. So the original graph need not be rigid. We're splitting it up into rigid subgraphs. Okay, and the original graph itself may have come with some as rigid subgraphs. So that's something that we are maintaining here. So This is called a pseudo-sequential DR plan. So now we need a definition of something called a branch in order to describe the algorithm. I'm getting to the algorithm. Okay, so the branch is so branch of a tree. So it's a branch of a tree is every node on the path from. So the branch includes the tree and 2 vertices on it. So every node on the path from A to B and their children. So in this case, you know, the branch here, you know, you can think of this as A and B, and here's your tree. This is your T, this is A and B. So basically you'll have all of the nodes from A to B and their children. So that's the branch. Okay, so these guys are not included in the branch. So the crossed ones are not included in the branch. So it turns out that the leaves of the branch are exactly the set of rigid vertex maximal proper subgraphs of A with A, you know, A minus B. So in other words, if you took the graph A and took away from it, cut away from it, the graph B, if you cut away from it the graph B, subgraph B, then the branch, the leaves of the branch, which means these black nodes here, we can show are exactly the rigid vertex maximal proper subgraphs or rumps of the graph that's left over after you've removed B from A. Okay. So this sort of tells us that if you can find the rigid vertex maximal proper subgraphs, you know, then you can sort of construct the, you know, sort of think of a wave going this way, starting from here, and you construct this branch, and for each of those, you think of its rigid vertex maximal proper subgraphs and go like this, and you can sort of construct this canonical pseudo-sequential BR plan in a kind of a wave going branch by branch this way. So once, and we can show that the rigid vertex maximal proper subgraphs, these black ones, can be found in time order v squared. So that sort of gives the sketch of the entire algorithm, which is what I'm going to do next. So we have to spend a little bit of time on this slide. So the algorithm, we can find the pseudo-sequential DR plan by computing the rigid rumps of G difference E for all E. You don't have to necessarily do all E, but in the worst case, you do all E. And doing a quadratic amount of work for each leaf. Okay, so here's the algorithm. You start with the G as the single node in the DR plan, right? So it has nothing else. And then the recursive step is you compute a branch for each leaf in the DR plan. So start with the, you choose an arbitrary leaf, and for each edge F in the subgraph that corresponds to that leaf, it could be a single edge, in which case, when you start right in the beginning, it'll be a single edge. So F in L itself is F. Then you compute the rigid vertex maximal subgraphs of the L, the leaf, with that edge taken away. And then for each of the rigid vertex maximal subgraphs, you choose an arbitrary edge G and compute the rigid vertex maximal subgraphs of L difference G, and then compute the branch from L to F. And this uses a linear number of graph intersections to position each leaf. Okay, so essentially, as I said, the algorithm sort of moves in a wave, if you will, going from one side, you know, one sort of path from root to leaf. It'll start with that, and then it'll find all these rigid vertex maximal subgraphs. And then for each of those, it computes a branch and so forth. So it proceeds in this manner. This is all the slides that I actually prepared. I wanted to quickly tell you a little bit about the original algorithm. So this is a much later algorithm. This was published in 2014 or 15 or something like this. But we had an original algorithm which may and we implemented it and everything. So I wanted to go and tell you roughly what that algorithm is like. So does anybody know a way of quickly scrolling down to? I guess not. Otherwise, I have to. So this is the software, by the way. We had software to solve these geometric constraint systems by using DR plans, 2D, two-dimensional and three-dimensional cases. Okay, so we had this other type of, so this is the complete decompositions are very similar to rigid vertex maximal decompositions, and the idea is more or less the same. So it's not the decomposition itself that's different. It's the, so as you can see the definition, we call it complete decomposition. This was back from 2001 or so. So is that either you have exactly two children and the children intersect on a non-trivial subgraph, and together their union is everything. Or there's the case two is if there's a, for each pair, they only intersect in a trivial subgraph, and again, each one of them is maximal. So we call that a complete maximal DR plan. But the key thing is that the building up of this was done bottom up. So the algorithm that we had, which we call the frontier vertex algorithm, to build this up, we did that, unlike the branch algorithm, which we now have, this was done sort of building up the whole thing bottom up, right? And this is showing, okay, after you get the DR plan, what do you do, right? How do you sort of use the DR plan to actually realize or find the solutions? So here's an example of which we call the Hextet example. And I just wanted to run over because we're going on and on about DR plans to at least get a little bit of an understanding of how we'll use the DR plans later, which is related to a lot of the questions that Alex has been asking. So this is a three-dimensional structure, by the way. So the D equals 3 in this case, unlike many of the examples I've been drawing recently, which are all D equals 2 examples. So D equals 3, so suddenly you get a, this you would consider to be over-constrained in 2 dimensions, but it's well-constrained, rigid, minimally rigid in 3 dimensions, the tetrahedron. So you can see this decomposition here. We got a tetrahedron here, another tetrahedron here, another tetrahedron here, a triangle in the middle, which is the green one, and then you've got these 3 pink triangles. Okay. So essentially, this is a canonical decomposition because you can't really do much better than this in 3 dimensions. Think of it. Remember that this is in 3 dimensions. So by saying you can't do much better than this is optimal. It's an optimal DR plan. It's also canonical. So once you have that, how do you then go and get a realization, or how do you solve the systems that correspond to this? So in other words, here we've got the system triangle, tetrahedron, triangle, tetrahedron, triangle, tetrahedron, and triangle in the middle, right? So, and this is a rigid vertex maximal. These are all rigid vertex maximal subgraphs. This is a canonical DR plan. It's optimal, everything. It's got the best thing you can have. So now you want to realize or find the solutions. So what you do is you sort of course, these are in R3, the coordinates of the points, and then the coordinates of point A, parameterized in C's coordinates, right? So C is the parent. Remember, Ci are the children. So you have a point, when you think of XACI, we're thinking of the points coordinatized within their own cluster or within their own subgraph. And when I say this, I mean that it's parameterized in the parent's coordinate system. And XACCI depends on rotation angles and will only be resolved into a final position XAC in cluster C by solving active constraints in C. We have the word called active constraints, and active constraints means that, you know, you have a subsystem that has already been solved, which means you don't really have to worry about most of the constraints inside that subsystem. But there are going to be some other constraints that are shared between subsystems, and those will come into play. So those we call active constraints at of a DR plan, right? So if you go back to the DR plan, so what this is saying is that, you know, if I now we're back to 2D again, these pictures, if we have already solved something, so in other words, I've already put these guys together into this structure, then the constraints inside the structure, in some sense, this is already, we have found the solutions to this. So this constraints that are not shared between these two structures that are required to then solve this system using the solutions of these two systems, those sort of inside constraints we don't care about. The only constraints we care by inside, I mean unshared. We only care about the shared vertices and shared edges. Those are what we call active constraints. Okay, so here we that's what we mean by active constraints here. So if you haven't, so let's consider the situation where we didn't have a DR plan, right? So just making it very clear why the DR plan is so crucial. So suppose you didn't have an unoptimized, sorry, we have the DR plan, we have the DR plan, but we're not thinking about it much further when we're solving the algebraic system. Okay, so you pick an arbitrary minimal covering set of clusters. In this particular case, say C1, C2, C3, cover all the vertices, right? So C1, C2, and C3 alone will cover all the vertices. You set the coordinate system C to one of the child clusters. So let's call it C1, right? So let's C1 be sort of like C1's coordinate system is now going to be the parent's coordinate system. And then we get C2 and C3's position and orientation within C's coordinate system by using a 3D composite 3D rotation matrix M and a translation vector T. So if you look here, so we have fixed C1 and we are now trying to position C2 and C3 in 3 dimensions. So you've got a rotation plus translation matrix for C2, rotation plus translation matrix for C3. You have to position it so that A and C, A from C, point A in C1 and point A in C2 coincide, point B in C1 and point B in C3 coincide, and point C in C1 coincide. But that's not just it. This is not a triangle, a 3D composable system. It additionally has all of these constraints. In addition, those constraints have to be satisfied. Okay, so so that's our active constraints. So the active constraints now between these 3 systems that have already been solved are the constraint that A is shared between these 2, C is shared between these 2, B is shared between these 2, and these distances have to be satisfied. I mean, have to be met. So you can, each of these rotations are basically can be written using the cosines of the different angles of between them, and then you just have, in addition, the sines and the cosines. You'll have additional equations of the type SI squared plus CI squared equals 1, because we want an algebraic system here. We can't have sines and cosines, so we just have an algebraic equation that forces them to be trig and trigonometric variables. So this is just standard rotation matrix. Okay, so so if you did that, you would get 6 active distance constraints for C, 3 distance constraints of this type. So what are the 6 active distance constraints? So we've got C1, C2, C3. I see only 3, this one, that one, and that one. plus, I guess, okay, so now we're writing the coincidence here as active constraints. Okay, so we will get 3 distance constraints plus these overlap constraints, which say that those A points, the coordinates of the A point in one cluster the same as the coordinates of the A point in the other cluster, same thing for B and same thing for C. And each of these is itself 3 constraints because there's 3 coordinates that you're equating. So you've got 9 constraints like this, plus you've got 3 more constraints like this. So altogether 12 constraints. Plus, of course, you also need the SI squared equals CI squared constraints. So those will be another, one for each pair SI-CI. But from the DR plan, from our DR plan, we can actually do quite a bit better than that. Okay, so here's what we do. So if the difference, this is a simpler example here, a simpler schematic showing the same example. So this triangle here just represents one of the tetrahedra. This triangle is another tetrahedron, it's just a rigid in 3 dimensions. These 2 share one vertex, these 2 share one vertex, these 2 share one vertex. And then you've got these 3 extra constraints. So instead of thinking about this as, what we did, which is think of this as sort of a rigid body, and you're sort of positioning this triangle with respect to this rigid body. It's got all of the rotations here, and with respect to those 3, instead of doing that, we can think of it as there's a rigid body in the middle, right? So it was in our DR plan, in our canonical DR plan, we had that triangle in the middle. So we take that triangle in the middle and we think of each of these triangles as, having 1 degree of freedom, or sorry, 1 rotation. It's like a quaternion that corresponds to a rotation about this edge, and same thing, rotation about this edge. And so basically we just have 3 variables, one each representing these three subsystems, plus a distance from here, distance from here, distance from here constraint system. So basically we have 3 variables and 3 constraints. So it becomes a 3-dimensional. So now instead of choosing, we're just showing this advantage of having these canonical DR plans as essentially capturing all the maximal subsystems that are there. So we can choose, instead of using just C1, C2, C3, we choose all 4, C1, C2, C3. It's not a minimal covering set. It's got more than just minimal. So, and then you choose one of them as the home cluster, the one in the middle. So C4 is the one in the middle. C4 is the one in the middle. You choose that. And so this tetrahedron was shown as a triangle in that schematic picture, but it's basically this tetrahedron. So so we do that, and then you use the basic trigonometry, and then as it's what I just said with using those 3 rotation variables here. And so using that, you basically end up with much fewer algebraics, much smaller algebraic system with only 6 constraints and 6 variables and all quadratic. Okay. So, and in the previous case, the degrees were also high. The reason is that you have those 3 distance constraints, where if you used all of these rotations and so forth, you have the rotation matrix here, which already is quadratic. The rotation matrix here already has all of these triples and so forth, degree 3 stuff in it. And so, and then you're squaring that. So you end up with much higher degree than you do if you do it this way. Okay. So you have this optimized algebraic system. So So in general, what you can do is take your canonical DR plan that you have and impose another combinatorial structure on it, which then allows you to optimize the way in which you actually algebraically solve that the systems that have been solve the systems at every node using the solved systems of the children. So so essentially that's the other thing that we will do. So essentially the remaining lectures on this DR will be split between D and R. This part that I have talked about, the last part of this lecture, are the recombination part after we have the decomposition. So once we have this canonical decomposition, there's a part that talks about, given that decomposition, how do you optimize the corresponding algebraic system that you will solve? That's the recombination part. And then the first part is, how do you even get the decomposition and optimal decomposition? So, and the first part is purely combinatorial. There's nothing other than graphs. The whole thing will be graphs, what we talked about here. And that proof, the key proof that we will do is that, this computing DR plan is in order V cubed. This is the key theorem. And the other theorem is that a canonical DR plan exists for a graph, and any canonical DR plan is optimal if G is independent. So these are the two proofs that we will do here. And for the recombination part, I have to tell you about this extra combinatorial structure that we impose on the canonical DR plan after we find it, which then allows us to optimize the number of equations and number of variables that you solve at every stage. By stage, I mean you have a parent and you have its children, and you're talking about how do you solve this. We've already optimized the minimum number of children and so forth, because the DR plan is optimal and it's canonical and everything. So now we are trying to figure out at that node how to place the children, solve the algebraic system that corresponds to that parent, given the solutions for the children. So, so these are the two pieces of D and R, and we're going to talk about both of them in the upcoming lectures. There's going to be something that I didn't yet say, which is here I talked about the top-down algorithm, and we're going to explain that further. But we'll also talk about the bottom-up algorithm, which is what the current code, some of the pictures that I showed, screenshots of this frontier vertex algorithm code, that's a bottom-up algorithm. In fact, while we believe that the bottom-up algorithm and the top-down algorithm essentially give the same, the bottom-up algorithm and top-down algorithm are based on slightly different definitions of the canonical DR plan. We believe that the two definitions are the same, but we haven't proved it. Okay. So one is based on, well, I won't go into the details. We're almost at the end here. And I'll just take some questions and then we'll go from there. Top share. Any questions?
Hello, Meera. I have a question.
Yeah.
So in your algorithm, you showed in the last minute. So the output is a polynomial system with lower degree than the original polynomial system.
It has both lower degree and fewer equations.
But it has the same number of the solution sets in the real field. It's the same as the original one.
Yeah, it's identical.
So
it's just
so
you're somehow how shall I say? You can write the same system in different ways. It's just a rewriting.
But the original one has a higher degree, right? has some multiplicities, right? You said the original has some degree 4 polynomials, and
yeah,
the output one only degree 2 at most.
no, it's more than degree 2. I think it's it's lower degree, but it's not 2. Let's see. So when we moved beyond when we moved beyond tree decomposable graphs, for tree decomposable graphs, you only have to solve, the decomposition is about as good as you can possibly get, right? So if you think of the tree decomposable graphs, and where was that? Share screen, go to the whiteboard. When we looked at tree decomposable graphs, in those decompositions, when you solve at any given stage, you're always solving one quadratic in one variable. Okay? So tree decomposable graphs are very nice, and it's a real triangularization. It's not a block triangularization. What we get from the DR plans is a block triangularization. And depending on how, and you cannot guarantee that you can solve only quadratics. I mean, you're solving eventually a system of quadratics, but then how you solve that block, you know, the recombination that I talked about a moment ago is how do you solve that block? So we can go back here. Maybe I can. I think it came from my moving this thing here. So if you think of this triangular tree decompose, this maybe I should spend some time next time. So there's a graph picture, there's a DR plan picture, and there's a polynomial system, what happened to it picture, right? So in general, you know, you have the original graph, and then you have the DR plan of the graph.
Yeah.
And then you have what happened to corresponding to the DR plan, the polynomial system, that the way you solve the polynomial system, right? So you can think of the DR plan as essentially talking about either in the case of a triangle decomposable graph, tree decomposable graph, you actually get this polynomial systems where each one of these is a quadratic in one variable after you have substituted in one variable.
Yeah.
And this is the case for tree decomposable graphs. Okay, if the graph is tree decomposable. If the graph is not tree decomposable, we are struggling, but we have managed to now define a DR plan. But the corresponding thing that it will give you will look like this. So at each stage you're solving not just one quadratic in one variable, but many equations here. Okay, you can, and these equations are now no longer quadratics. Like you can see some of them are quadratics, but then you also have, you know, when you have this situation where you had 3 rigid objects which are you know, coincident on these points, and then you have some extra constraints like this, whatever. So these are quadratics, but then they are based on this. But then this thing here, you have this rotation matrix that corresponds to this guy, and you know you need to use the rotation matrix to get the coordinates of this point, and then when you equate them, you get cubics there. And you know, it depends on whether you're talking about quaternions this way, or how you express this will change. And so this, in any case, this block that you're trying to solve here may not be quadratics. Now you can rewrite it, right? So that by rewrite, I mean, you're not changing the solutions, the real solutions. Okay, so the real solutions are exactly the same. And you can do it in multiple ways. And what I was talking about at the end, and that part of it is what we call the recombination part. And this part, you know, how you rewrite makes a big difference.
Yeah.
And that's the part, that's another optimal recombination, which we can also attack in a combinatorial way by imposing another combinatorial object on top of this canonical DR plan. And we'll come to that later. Okay, so so you have some properties of the graph, you have some properties of the DR plan, and correspondingly you'll get other combinatorial properties of the actual. So this block here, what I have here is in what I'm talking about in the block is just solving, knowing the solutions of all of these systems in the DR plan, solving this system, which is the union of the children, right? Just that part is what I call recombination. At any given stage, you're using the solutions of the children and coming up with the solution of the parent. So just this one block. So that block, optimization of the rewriting of that block is what we call the optimal. I mean, it has its own combinatorics that you can optimize. And that's what we're gonna, and it has its own underlying matroids and stuff, by the way. And we have some couple of papers on that. So I'll talk about all of these, coming up. So this is the good, easy picture. Everything is easy in this case. Coming up with this is easy because, as I said, we'll spend a little more time on 3D composable graphs when we come to the next topic on under constraint or flexible graphs and how do you find the configuration spaces of them. And there, we'll talk a little more about how quick it is to find a DR plan of these 3D composable graphs. It's very fast because you can finding these 3 points that you can partition. There are many such 3 points that you can partition, but the key beautiful thing is that it really doesn't matter what you pick at the first start. It has what is called the Church-Rosser property. So it has a very fast algorithm for coming up with a decomposition. And then after you have the decomposition, there's nothing to be done really. It just breaks it down for you right away. But not every graph, there are very few graphs of this type. So this is just an attempt to generalize, and it gives rise to many nice, interesting combinatorial problems.
So may I ask also a question?
Yeah.
I wanted to maybe to just make clear how can we know if a graph is 3D composable?
That's what I was just talking about. The recognition of whether a graph is 3D composable is exactly the same algorithm as coming up with the 3D composition of the graph. Okay. So there's I wasn't going to spend time on that right now because we're going to spend more time on 3D composable graphs later. And another reason I'm not going to spend time on that right now is because it's so special that it does not generalize. Okay. So it's a paper by Fudos and Hoffman, I think, where I will try to put the where they show that how to find these 3 vertices that split the graph. And there are many subsets, many possible triples of such vertices, but they show that it doesn't matter which you take in the beginning. That you greedily choose 3, right? And then you proceed in this fashion, and then you can show that if it is 3D composable, you will find that out, and at the same time you've produced the DR plan for it as well at the same time.
Perfect.
Does it make sense?
Yeah.